Calm. You might know why you're here already. I don't want to just say nothing. Alright, cool. So we've got a situation here, paracetamol being made, whatever. Um, it says name the mechanism in step one, yeah. Well, obviously, in step one, we got hydrogen that's there, that's being substituted for NO2. So obviously that's electrophilic substitution, yeah. So just write that. Yeah, and obviously that way you can tell is because it's an arene bullshit, yeah. So therefore, if it's arene, obviously it's gonna have like something to do with electrophilic substitution, yeah. That's the only mechanism that you know in this situation anyway. Alright, calm. Another thing as well is gonna be but you can tell that NO2 was NO2 plus in it, and that's an electrophile, it's positive, and then you can see it got substituted for H, yeah. So that's easy, bro. You get me, yeah. NO2 plus, obviously that's nitrification, yeah. Alright, cool. Safe. Complete the equation for the reaction in step two, yeah. So let's look at step two. We're going from NO2 to NH2, yeah. So obviously it's being reduced here. If you don't know about reduction, reduction would be the, negation of oxygen or the addition of H2. So obviously we're adding H2 here, or in this case, replacing O2 with H2. So therefore, obviously what we're gonna do here is in reduction, we're gonna need to add hydrogen and then take away the oxygen in it. So the steps this would actually go by, just so you can understand like the process behind it, so you can think about it in real life here. Because if I just write the answer, you might be like, yo, but how did that occur in it? So it's good to understand the shit behind it so you can do it in real life and shit. You get me? Alright, cool. So let's say NO2, yeah. That's what we got right now. It needs to be reduced here. So what's gonna happen is gonna fuck off the NO, one of the oxygens, which is that, and then it's gonna turn into N, and then you're gonna add the hydrogen to that, so NOH here. And then obviously the oxygen is gonna be reduced again, so it's gonna get rid of that shit, and you're gonna get NH2, yeah, as the final answer. So that's how it's going to go from there to there. So effectively what's happening here is you're adding hydrogen and removing oxygen. Oxygen's not going to remove on its own, is it? It's going to remove with hydrogen as well. So you'll have excess hydrogen here. And so we can therefore determine here that obviously we're going to be adding H2. And obviously we're going to be removing the H2O here. Now you just need to balance shit. So, well, fuck. Yeah. Listen, bro, how many oxygens got removed? Two oxygens, bro. So therefore you need two oxygens here. So add two there. And then there you go, bro. And then how many? So that's two times two is four, yeah. You're removing two of these as well. So that's four plus two of these, which is six. So here you're gonna need three. Six got added, yeah. So six got added, two remained, and the other four got fucked off with the hydrogen, yeah. Alright, cool. Alright, safe, bro. So here we got a situation. We got this obviously, yeah. Alright, cool. So in theory, either that or that can be used in step three. Alright, listen, bro. Just ignore all of that, yeah. Just get straight into it, yeah. Don't be a pussy, bro. Okay, so this obviously turns into what, fam? We're gonna get CH3, yeah, C, Cl. I'm just copying it off here. That double bond, yeah, went onto O, yeah, so that's gonna become one O. And then obviously the pair of electrons, yeah, went onto O, so therefore it's gonna become two electrons on there, yeah, with a negative symbol as well, because now it's negative because the electrons went onto there, yeah. Alright, safe. And then also, yeah, this is nucleophilic addition elimination, innit? Because addition there, nucleophile got added, and then you got elimination after you're gonna remove something in it. So obviously, yeah, that got added there. So if you know the mechanism, you can kind of memorize the arrows, or you can kind of just freestyle it like this, yeah. Safe. So now what's the situation here? Obviously, electrons got added onto C, yeah. So that means that NH2 lost a lone pair of electrons, which means that it's gonna get rid of the this is not H, is R, by the way. Which means it's gonna get rid of the electrons, gonna become positive, yeah. So N is positive now. Alright, safe. So what's gonna happen here, bro? Obviously, well, shit. If we look at the original expression over here, the thing that we're trying to create, yeah, it has no Cl. It also has the O double bond, yeah. So that's a bit of a like a giveaway in it. You get me? Obviously, Cl is gonna fuck off here, so electron's gonna go from that bond onto Cl there. There's no need for Cl to be there. And then obviously also here, the electrons are gonna go onto the bond like that to reform the double bond because that's unstable. You can't just have O with two electrons just chilling like that. You get me? So therefore, it's gonna go onto there. Cl is gonna fuck off. What else can happen? Obviously, we got this situation here. If you look at the original expression as well, you'll see that there's only one H on the end. There's not two H's. So therefore, what's gonna happen here is this thingy, what the fuck do you call this? Hydrogen, yeah, is gonna the electrons from there obviously going on to N plus because it's N plus. It needs to reform that. It can't just be N plus. Come on, yeah. So obviously hydrogen needs to go away. So it needs to give that the electrons from the hydrogen, and so that hydrogen bond is gonna get destroyed as well. And then obviously as well, uh, you're gonna need the H to be carried off by something. You can't just have H on its own. Obviously, there's a Cl there for as well for that kind of purposes for HCl. But another thing that is going to be there as well is it reacted with this 4-aminophenol. So there's going to be excess of that. There's going to be multiple of that. So then therefore the the N2 2 dots H2 yeah is going to obviously react with the H yeah. Since we got the two lone electrons there, that's going to combine with the H to then have NH3 onto that. And that's obviously the end of the mechanism right there, bro. Yeah, that's the situation there. You get it. Alright, cool. In practice, ethanol anhydride is used in industrial synthesis rather than ethanol chloride, yeah? Give one reason why ethanol chloride is not used in the industrial synthesis, yeah? Well, obviously it's not used because it's very dangerous, yeah? So it's corrosive or whatever, innit? So very dangerous to use, yeah? Alright, safe. In step 3, other aromatic products are formed as well as paracetamol. Draw the structure of one of these other aromatic products here. So if you look at my man over here, what he's saying is that in this step 3, yeah, obviously down there it said that you could use either one in it, some shit like that. Yeah, you could use ethanol anhydride, yeah, or ethanol chloride, yeah. So he used the amniphenol, yeah, with ethanol chloride, yeah. So ethanol chloride that he's using here can react with this as well. So therefore, if ethanol chloride is being used, that's going to be what CH3 C CO Cl, right? So what's going to happen here is basically the COCH3 would add to the O to make like an ester kind of link, and then Cl would react with H to make HCl. Does that make sense? So that's effectively what's going to happen. Yeah, it's going to react with that OH species there. Yeah. So therefore, what's going to happen? The product of that is going to be what, bro? The product of that is going to be the same shit as we had last time, the same kind of product here. So, bro, this is barely any, my handwriting is shit as well, like, bro. Alright, there. And then the O, that's the O from earlier. The H is going to be replaced by all of that shit, yeah? So the C double bond O, and then the CH3 from, because it's ethanoic, yeah? And then, yeah, and then it's going to produce HCl as well. And then, obviously here, it's just the same as we had last time. Yeah, I don't think I drew the product of last time, by the way. My bad for that. I'll add that here for you, look. What you're producing here is the same shit as in the question that's attached to the arene, yeah? It's that. Alright, calm. So effectively, I'll write that here. So you're just making that again. So HN C double bond O CH3, yeah. That's the answer. Alright. Chemists have recently developed whatever two-step process. Complete the equation for the second step here. So what's actually going on here? Hydro is going with ammonium ethanoate, yeah. So hydroquinone, yeah, is mixing with that shit to make something, yeah. So obviously what we need to do here is we need to therefore write what it's reacting with here. So obviously we got ammonium ethanoate, yeah. Ammonium is NH4 plus here, and ethanoate is CH3 COO minus here, just like ethanoic acid without the H here. So it's just that. Alright, calm with that OH. And so we got NH4 plus here. Alright, safe. So that's mixing with that, yeah, to form paracetamol, yeah. Alright, cool. So think about this, yeah. What has been made here? We got OO and O, and we only got one O left. So therefore, we're removing oxygen here. And obviously, oxygen is going to remove hydrogen always. Yeah, that's like the basic rule, bro. Let's be real. And also, you're adding bare hydrogens here, and I don't see the hydrogens here translating, bro. I don't see them over here. Do you see them, bro? Do you see the hydrogens? No, I don't think so, bro. So therefore, it's going to be H2O, innit? That's what's going to be released here. How many oxygens got removed? We got one remained, so just two basically. So two oxygens got removed here. Because if you think about it, we added two there, and there's only one remaining. Which was already there. And hydrogen, yeah. I mean shit, I mean that's probably balanced, bro. Let's be real. If you add it to oxygens, it has to be balanced. Two times that is four. We added four H. The one H remained. So therefore, yeah, bro. It's four H as well, innit? So two H2O, bro. That's it. Alright, safe. Calculate the mass in kg, yeah, kilograms, bro. They're whipping kilograms of this shit. You know what I'm saying? Yeah, you're out here making grams in your little chemistry lab, yeah. They're out here whipping kgs, fam, yeah. Turning grams into kilos, you get me? Of hydroquinone, yeah. to produce 250 grams of kilograms of paracetamol, yeah, bro, it's a waste of paracetamol, fam, yeah, paracetamol doesn't even fucking work, bro. You know what I'm saying? Shit's a scam, bro. So let's take, what are we doing here? Why the fuck did I go back here? Oh, yeah, yeah. Alright, so cool. So, obviously, we need to find the MR paracetamol, yeah? So to do that, it tells us the, MR of this other shit of hydro, yeah? Hydro is 110. So therefore, yeah, so you just need to, take the OH here. So obviously this is 110 here. So therefore take away the O. 110 minus, let's do this together, yeah. 110 minus 16 gives us 94, yeah. Then the H remains, don't need to take away that, yeah. Add 12 for the carbon, add another 16 for the oxygen below that, add another 12 for the other carbon, add 3 for the other hydrogen. Shit. And I forgot about the N as well. And then add the nitrogen that got replaced by the O, yeah. So add that, that's another 14, yeah. Alright, that's 151. There we go. Alright, cool. 151, yeah. So therefore, N of paracetamol, yeah, I'm even gonna write that, you get it, yeah, is equal to 250 kg, yeah, that's just 50 grams, yeah, over 151. That's gonna get you 1655.6 moles, yeah. Alright, safe. So that's how many moles you got, yeah. Now you need to find how many moles of hydro, yeah. So this is a 1-to-1 ratio, yeah. So 1-to-1 of hydro, as seen from earlier. So that's 1-to-1 of hydro. So the hydro is gonna be what, bro? Hydro is gonna be also the same amount of moles, 1655.6 mole. So therefore, to find a mass of hydro, yeah, you're gonna need to do M is equal to moles times MR, yeah. So that's gonna be 110 times 1 point. You divide it by 1,000 now anyway, because we need to do it in kg, yeah. So instead of doing times 1655, just do times 1.6556. And that's gonna give you 182. So that's the kilograms, bro. 182 kg, yeah. Safe. Alright, safe. Here we go. Question 2, yeah. The reaction between propanol chloride and benzene is example of acylation, yeah, which is the correct presentation. So this acylation on a benzene ring, yeah. So obviously this is gonna be proper acyl chloride, yeah. So this is gonna be Friedel-Crafts acylation. So obviously it's C in it. Yeah, that's the first step of Friedel-Crafts acylation. If you look and you memorize the mechanism, yeah, the first step is the thing inside of there is attracted to that like a nucleophilic substitution. Yeah, so that electrophilic ring is attracted to the C plus. So that's gonna be the answer. Alright, safe. Question 3A. Explain in terms of bonding in the shape and compare the stability. So you need to do each one. This is a 6 marker, yeah. So you need to do bonding, then the other thing, then the other thing, yeah. With the hypothetical, whatever. Use the data in your answer, yeah. So listen, bro. Do this the way that I do it, yeah, which is to write like a big paragraph in it. You get me, yeah. That's gonna show him that like that you know what you're talking about, which means that he's gonna like less obo in it. Alright, calm. Look. So basically, each carbon, yeah, atom forms 3 covalent. Listen, I don't like not talking for too long here, so I'm gonna talk a little bit here. So write this out here. So each carbon atom here forms obviously 3 covalent bonds here. That's what's going on here. And then the fourth one is the outer electron here of each carbon here, which is going to be in the p orbital here, which is above and below the plane here. And that's going to overlap with the adjacent p orbitals here to make the delocalized ring of electrons here, which they call it a pi cloud here. Pi being like this, yeah, of delocalized electrons above and below the plane of the ring here. So that kind of answers a few of what they want, a couple marks there, yeah. Then what you want to do is you want to mention delocalization, yeah. So I haven't really said it outright. That's going to be the third mark here. And now you can start talking about the shape, so you can like lean that into the shape, you get me? Yeah. Obviously, they want to hear you say planar, and they obviously they want to hear you talking about hexagonal ring, yeah, and obviously as well bond angles as well, yeah, with a bond angle of 120 degrees, yeah. So as a planar shape, obviously it's planar because of the bond angle, because of the delocalization, yeah. That's why it's planar. Otherwise, it wouldn't be planar because you got all this random angle with lone electron repelling bullshit. But because you don't have that anymore, because delocalization, that cloud that's formed, yeah, it's effectively just like a normal hexagonal kind of shape, so 120 degrees, yeah. And the CC, so that's the next piece of information, yeah. And then to get that 6 marks nicely, yeah, you want to put the expect. You want to start talking about stability, yeah. So the expected enthalpy change of hydrogenation, yeah, of cyclohexatriene is obviously minus 360, yeah, kilojoule per mole. The actual energy change, enthalpy change of benzene is less exothermic by 152 kg per mole, yeah. Now, saying it's less exothermic here, listen, you could just say, yeah, that this is minus 208 and this is minus 360, but saying it's 152 uh kilojoule per mole less exothermic here proves that less energy was released, which means less bonds were made, which means that less was broken, or means that more energy was retained, or it also means that benzene has lower energy and hence is more stable than cyclohexatriene. Yeah, and that's it for the 6 marks. That's gonna get you 6 marks guaranteed, bro. Straight out the bat, full. You know what I'm saying? No question about it. Alright, calm. The enthalpy of hydrogenation of cyclohexadiene is not exactly. So you're saying now let's look at the dienes, not three double bonds. Let's say that we get um two double bonds. Also, you can say this is due to delocalization energy at the end if you want as well. Anyway, yeah. So it's not exactly double that of cyclohexene. Yeah. So just the enthalpy value. So you just need to do double that. Yeah. So it's going to be between minus 120 and minus 240. But obviously, like minus, you get what I mean in it. You can't count 120 or 240 either. So it's going to be between them, yeah. So between them is going to be what, bro? Just get any value between them will suffice here. I'll just say minus 175, yeah. And what I'm going to say here as well is to justify your answer, yeah. The CC double bonds are separated obviously by a CC bond there, same way they're alternating, yeah. Same way like in benzene or in any of this shit in cyclo hexatriene as well, yeah. By CC single bond. This allows for some overlap of p orbitals, yeah? So the p orbitals are still going to be overlapping somewhat, so it's still going to have some kind of delocalization effect here, not as much as in cyclohexatriene, yeah, but still enough to, to do something in it to lower the enthalpy value. Alright, cool. The nitration of benzene uses a nitrating mixture of concentrated nitric acid and concentrated. Okay, so this question, yeah, you might be thinking, yeah, which one's correct here? I can't lie, this is a bit of a bullshit question here. The first time I read this, I was getting confused. Even me, bro, I was confused. Until I clocked here that H2SO4 here has lost the hydrogen here. So because it's lost the hydrogen, that means that it was acting as an acid here. And so this shit must be acting as a base. We are probably thinking, how the fuck was it acting as a base? Because it went from HNO3 to this shit. And that's not what base does. Do you know what I'm trying to say? So what happened here is it accepted the hydrogen from the H2SO4, so it acted as a base, and then it dissociated to make this shit. So it's in like two steps. You get me? So that's why answer A is correct, even though it might not be obvious. So yeah. Alright, so this question is about nitrobenzenes here, whatever. Write an equation for a reaction of concentrated nitric acid with concentrated sulfuric. Listen, boys, listen, boys, listen, boys. What did I tell you, yeah? In the video that I uploaded about this whole thing, yeah? About like learning aromatic chemistry, yeah? I told you, man, yeah? I told you, man, to memorize the equation, because I told you they're gonna ask you for that, yeah? And look what they asked you. They asked you concentrated nitric acid with I stop being a prick. The equation you need to memorize basically is H2SO4 plus HNO3 is going to get turned into H2NO3 plus HSO4 minus, and the second equation is H2NO3 plus, so the thing that you made is then going to dissociate to make H2O plus NO2. So the equation they're looking for here is the overall equation, yeah? So you just need to memorize this H2SO4 plus HNO3 is obviously going to produce the species they want to produce here is obviously NO2 plus, that's the, you know, nitro that's going to react with the thing here, nitronium ion that's going to react to make nitrobenzene, and then HSO4 minus plus H2O, yeah. And this H2O and NO2 plus, they came from the first equation here, which you can produce here, which is H2NO3, which is going to dissociate into that. So you could write it as those two separately, you can write it combined like this, or you can write it with H3O as well, and that sort of shit. Alright, name and outline a mechanism for the reaction of the species between nitrobenzene to form 1,3-dinitrobenzene, yeah? Okay, calm. So we're looking at 1,3-dinitrobenzenes, yeah? So it's going to attach on the third one, yeah? So basically, let's just draw, first name it, yeah? Obviously, it's electrophilic substitution, bro. What else is it going to be like? Come on. It's literally given to you. There's the only reaction mechanism in this whole fucking chapter, yeah? Not only that, but also, like, it's literally an example of a mechanism you already know. Like, it's literally, you should know this step by step. It's just the nitrification, yeah? Alright, safe. So the mechanism, yeah, is obviously yeah, so draw nitrobenzene in it. So you get that NO2. Come on, come on, come on. Alright, cool. So you're gonna add NO2 to that. That's the electrophile here, bro. So that's the situation there. Obviously rings attracted to that, so that goes there. Next step is gonna be obviously redraw the same shit. So there you go like that. Bang, bang, bang. Extend that. Extend the clip. Yeah, come on. Yeah, I don't know why I drew the full circle. I'm stupid sometimes, bro. That's just how I am, bro. I'm not a very smart guy. Draw NO2 up here, yeah, and then obviously NO attached to the third one. So that's 1, 2, and then 3 is gonna be down there. I know I drew it a little bit like, yeah, you get the point, fam. So then NO2 is coming off there. Obviously H was on there originally, so now you got a bit of a situation now. NO2 has been attached. Obviously the ring has been reformed. Now again, draw it up to the adjacent ones here. Don't draw it past that, otherwise you might lose a mark here. And now obviously, yeah, this bond electron is going to move into the middle to reform that ring. So now obviously you're going to get final product, which is going to be NO2. And then obviously just a simple situation here. So that, 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 bang, and NO2 here. Alright, cool. And then plus H plus here. Alright, safe. See, yeah, there's a lot of waffle going on here. So just look at the question. Use the chromatogram, yeah, in the experiment above to find dinitrobenzene experiment, yeah, the RF value, yeah, the RF value here. Obviously, it's not gonna, RF is just what, bro? RF is just gonna be um distance of dot from start line divided by solvent front, yeah. So it's pretty easy here. Just take this distance here. Don't know why it's breaking up like that. So take that distance there and then divide it by that distance there. I hope it didn't cut out the mic or something. And then yeah, you'll get your answer basically, bro. And that's gonna the answer that you're gonna get is 0.41. I mean, sorry, D, yeah. So that's 0.62. Obviously, I haven't got the I haven't got ruler and shit, so can't really do. I mean, I got this, but let's be real, that's not accurate. Come on, you get what I'm saying? So yeah, alright, safe D E, yeah. Alright, cool. So what does it say? Say in general tells us what the terms of distance traveled by spot. Yeah, so obviously if the spot is traveling and shit, obviously that means that it's what the terms is how soluble it is. Yeah, so solubility in the mobile phase. Yeah, so the mobile phase is the shit that's moving the solvent. And also retention. This is important. Some people miss this out. You need to say also the retention or the affinity or the like likeliness, yeah, because obviously it's gonna want to stick to the actual stationary phase as well, yeah. So you need to say that as well. So it's not only the solubility, it's how soluble it is in the mobile phase and also how much it wants to stick down to where it already is, yeah. So that's also part of it. Some man forget that. Alright, calm. I think you needed both of them things to get the mark. Obviously, you just fucked off, but who cares, man? Alright, cool. E. To obtain the chromatogram, the TLC plate was held by the edges and placed in the solvent in the beaker in a fume cupboard. Yeah, the lid was then replaced on the beaker. Give one other practical requirement, bro. So the other one is just bait, bro. You know this since GCSE, so obviously it's solvent below start line. Yeah, obviously it can't be above the start line. The other one is the thing must be in pencil or not in ink or whatever. Yeah, whatever. Alright, cool. But that didn't get you marked then. We didn't really mention that some shit. I don't know. Alright, cool. A second TLC experiment, yeah, was carried out using that and that. Okay, it doesn't matter, bro. Deduce the relative polarities of the 1,2 dinitrobenzene and the 1,4 dinitrobenzene. Explain why 1,2 has a greater RF value, yeah? So, oh, okay, yeah, that doesn't place that. Okay, so it's found to be greater, yeah. So 1,4 is a greater RF, which means that it traveled further, yeah. So deduce the relative polarity. If it traveled further, yeah, that means that oh shit. But it's hexane, yeah, was the solvent in it. So hexane was a solvent, yeah, which is non-polar. So therefore, yeah, always, yeah, soluble. How do I say this shit? The same polarities dissolve in each other. Yeah, there's a nice way to say it, but I don't know. Just learn it like that, yeah. If something's polar and something's polar, they'll dissolve nicely. If something's not polar and not polar, it will dissolve nicely. You get it? And not polar doesn't dissolve with polar, and same way otherwise. So therefore, hexane is not that. It's not obviously hexane is not polar, bro. Yeah, let's use our logic here. Yeah. I say no, hexane, whatever the fuck we use, is not polar. So therefore, if we got something here, it's also not polar. Yeah. So therefore, 1,4, the 1,4. I'm not gonna write out the whole thing. Just the 1,4 is less polar. Yeah. So because it had a great RF value, so it was more polar. It was more soluble, yeah, in the non-polar solvent, which means that it's non-polar. You get it. And the explanation is I actually shit. The whole time I had the explanation right here. Yeah, in the solvent. Yeah. So if G. A third experiment was carried out. A student stated that the RF value of 1,2 is in the third experiment would be greater than the 1,2 in the experiment part F. What changed exactly? I played. But the solvent is a mix of hexane and ethyl ethanoate. Yeah, alright, safe. So, um, 1,2 was more polar because we just said that 1,4 was less polar. Yeah. Now we're mixing in a actual polar substance here. F for ethanoate. Obviously, it's got polar bonds, bro. It's got O double bond and it's got a H bond. Yeah. So therefore, we're using a polar solvent now. So therefore, the brother is actually correct first time. The brother is actually correct here. Okay, so we'll move further than the 1,4, or than the last experiment, because obviously it's more soluble, yeah? Alright, safe. Is that really the end of that question? Yeah, crazy. Alright, safe. G. I mean, question 6. Use your understanding of bonding and benzene to identify the compound that has the most exothermic enthalpy of hydration, yeah? So the most exothermic enthalpy of hydration means it's going to be the less stable, because if you have a more exothermic enthalpy of hydration, it means you're less stable. Do you get it? Because remember last time with the like benzene shit, yeah, obviously benzene like not differentiates it. Benzene like it has a higher value than expected, yeah, because it's more stable. So therefore, if it has a lower value, more negative value, more exothermic, it's going to be less stable, yeah. So which one here is less stable? It's going to be the one with no delocalization effects. So that's obviously going to be A. If you don't know why it's A, then B, C, D all have like the same delocalization effects pretty much here. Um, a good way to know it is like if there's more distance between the double bonds, that means that there's going to be more delocalization effects here. So effectively, I mean less delocalization effects here. So they're closer here, it's going to overlap. Here's pretty close, gonna overlap. Here's gonna overlap. The only one that's pretty far, these two on opposite ends, is not gonna be much overlapping, so there's not gonna be much delocalization effects, which means that obviously the energy isn't gonna be brought down. So it's gonna be more exothermic here, less stable. Yeah, you get it's more. You can think of it as well. Instead of thinking like that, you can also say that it's the electron density is more localized. Yeah, so it's more localized compared to delocalized. Compared to a spread or next to each other like that, they're localized in different spots here. You get alright. So we've got some situations here. Yeah? Name and draw a mechanism for the reaction in step one. Yeah. So in step one, we got that go into that. Yeah. That's gonna be nucleophilic addition and elimination because you're gonna be adding shit a nucleophile and then eliminating something. That's the only other. Listen, if you've got a benzene ring, yes, either two things. Yes, either electrophilic substitution, yeah, or nucleophilic addition and elimination. If it's not if it's not obviously some kind of substitution, yeah, like what's happening in step two, yeah, where hydrogen's been substituted by NO2, then it's the other one, bro. Alright, cool. So name of mechanism here is yeah. If you're adding some shit to it, it's gonna be nucleophilic addition elimination here. Alright, safe. So the mechanism, I like how it just disappears, just like it's just telling me to fuck off basically. It is what it is. So basically, yeah, it's like we did earlier. So that. Um you've got NH2, obviously the nucleophilic part is this N with the two dots. That's gonna be nucleophile situation. Because you're gonna have a C here. ClOO CH3. And it's the same as last time, bro. So the two dots are attracted to this nucleus here, so it's attracted to the C. And then same as last time, bro, where we had the first step, this double bond's gonna break, it's gonna go into the O. And then now it's like last time they gave us that first step here and they told us to do the rest of it, yeah. So it's gonna be exact same process here, bro. So just learn this mechanism and you'll be good. That's gonna be HH. We said the two dots because we lost a lone pair, it's now positive, bro. So it's gonna be plus CCl is still there. Or obviously the lone pair went onto that, so we can put lone pair and negative, and then obviously H3C here. And now all you wanna do now is simple, bro. This obviously we know this is gonna return here. This is gonna break that, and then this is gonna go into the. I know I'm kind of rushing it, but you get the point. And just to show them that you know what you're talking about, yeah. Same as last time, yeah. An extra NH2 because an excess here will come and it will also take away this hydrogen here because the hydrogen can't just go by itself. So that's gonna go into there, yeah. Alright, safe. So that's what happens here, bro. And then you're just gonna get the final product in it, which is gonna be. I know I rushed through that, but it's the mechanism, bro. Like I explained it earlier a lot longer, so can't. I think you might know by now. That's M, that's H, that's CO. Don't know why I did that. H3C. That's it, I like. Yeah, that's it. Alright, come on. So that's the final product. Alright, cool. B. The product step one was purified by recrystallization or whatever, bro. Give reasons for each of the following practical steps here. The minimum quantity of hot water was used here. So if you're looking at recrystallization, yeah, essentially what you want to do, um, you want it to recrystallize, yeah, which means that you want it to crystallize, yeah. So you want the shit that you're dissolving into it to be fully dissolved into it, yeah, to form crystals, yeah, not just to evaporate water, yeah. So therefore, what you want is to ensure, saturation, yeah. So you want them to be saturated so that it actually recrystallizes and you form crystals, yeah. Alright, calm. The flask was cooled to room temperature before the crystals were filtered off, yeah. It's higher yield, yes. The more you cool it, the more yield you're going to produce, the more crystals you're going to make, yeah? So higher yield, yeah? Alright, cool. The crystals were compressed in a funnel, yeah? This is a bit fugazi, I can't lie. This is a bit stupid, yeah? But the reason is obviously because, to remove, it's because it allows it, yeah? To dry out. The reason for that is obviously if you compress it in a funnel and you put a cork in there or whatever, it forces all the water out of the crystals, yeah? So it's going to dry better, innit? Alright, cool. Little cold water was poured. I like how they say a little cold water. You know, a little cold water was poured into through the crystal. Yeah, shush, man. It's to remove any soluble impurities, yeah, because any soluble impurities will just dissolve in the water and fuck off. You know what I'm saying? Also on top of that as well, another thing that you might want to note, yeah, is that you see these questions, yeah. I can't lie. I think if you there's people out there that have done it, yeah. If you go through all like the practical, there's like certain shit you need to know. I think it's on like Reddit or Student Room, whatever, yeah. There's like shit that you need to know like this, which is where you're gonna get these things from, yeah. It's not bait in the course, yeah. You might need to go look at that before the exam, and you'll know that how to answer this. Do you know what I'm saying? I can't remember it. I just remember from back when I was doing it, certain man were doing that. You get me back when I did the paper. Alright, safe. Question C, yeah. The melting point of the sample in part B was found to be slightly lower than the data book value, yeah. So just the most likely impurity to have caused low value. They didn't really dry this like to a valid amount, yeah. So obviously it's gonna be water. That's the only impurity that's gonna be there that they didn't mention and shit. So it's gonna be water, yeah. So how to do it? You can basically just say leave it out in air for longer. That's a valid response, yeah. Or you can say press the sample between filter paper if you want to like guarantee to get the mark, you get me? Alright, cool. Uh that's the repeat. Alright, D. An experiment starting with that. That was purified, so just start by finding the MR of both of them because they don't tell you the MR of anything here, bro. So we're looking at step one here. So you just want to take MR of that and MR of that. So let me just write that quickly. So we got C6H5, that's the benzene ring if you man don't know. That's a quick way to write it. NH2, so basically just do the benzene. I just add these together, you get MR of 93. I actually did it, so it does get you that. And then the second one here is the product they're forming. That's just again the benzene ring here plus COCH3 uh NH actually. Don't know why I missed that out. Again, add that together, bro. I also added it. It gives you 135. So there you go, bro. So you got 93 and whatever. So now let's find the moles of the phenyl, amine. So the phenylamine here is this shit here. That's gonna be it tells you is 5.05 grams. So it's 5.05 over 93, which is gonna be 0.054 allegedly. So that and yeah, cool. It's a 1-to-1 ratio. So that means that the mass of the other shit of the product that you're making here, M of product here. So not N, but M, yeah. So mass of product here is going to be the moles here. So 0.054 times by the MR. So 135. That's going to give you 7.33 grams here. So now all you need to do to find the, since the theoretical value, yes, all you need to do to find the percentage yield is find the real value here over the theoretical value of how much you produced, which is that's amount of product theoretically times by 100 here. That's going to get you 65.8%. So that's what that is over here, 65.8 here. Alright, safe. Alright, E, yeah. A reagent for step 2 is a mixture of concentrated nitric acid with a concentrate sulfuric acid which react together to form. Alright, bro. Write an equation for the reaction intermediate in step 2, yeah. So step 2, bro, this is bait, bro. Nucleophilic substitution. You already know what's going on here, bro. Nothing really to say. So nucleophilic substitution, you're adding this to NO2 plus, and you're getting this, and then the hydrogen is obviously got removed in it. So that's all you need to write. Just that plus the electrophile and whatever's made here. So simple, fam. All you need to do is bang, 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 and then circle, and then NHCOOCH3. It's not OO, I always write OO, for that. Alright, plus NO2 plus here, gonna make that. So NHCOCH3 here. And then obviously nucleophilic substitution, so it's gonna be that. I mean electrophilic substitution and then H plus is removed here. So that's the electrophilic substitution here. I name the mechanism here, I've said it like 50 times now. So just the type of reaction occurring in step 3. What's step 3, bro? So you got this turning into that. That's obviously reduction, yeah. But you need like a strong reducing agent for that. So I think yeah. So obviously what they want here is going to be hydrolysis, basically. Reason for that is because this is like an acid, a weak acid kind of shit. So you're gonna obviously react that with water, and the water is basically gonna break it down, yeah. So into just H2. You get me? And it's gonna fuck off. The rest of the water is gonna fuck off with that COCH3. So it's going to remove that with it, and it's going to give it H, if that makes sense, yeah. So it's effectively like reduction, yeah, in a way. Yeah, so that's hydrolysis, basically. You're using water to break down a compound, yeah. So therefore, yeah, you get it. So that's what that is there. It's not too big though, can't lie. You could easily miss that mark, really and truly. It's not too important. Identify the reagent using step 4. Step 4 is just a situation. It's just when NO2 turns to NH3, bro. NH2, I don't know what chapter that's in, bro. Yeah, I think it's in the Amy's chapter bullshit. That's just tin and HCl in it. Yeah, so SN and HCl, yeah. It's not in this chapter though, it's in a different one. So if I didn't mention that, then I didn't mention that. But it's in the all equations you need for A-level chemistry, whatever I called it, it's in that video. So yeah, SN and HCl, yeah, is what's needed to catalyze that, yeah. Alright, calm, and that's it, man.
I started with 0 contacts in my bricky, now it keeps calling me. M-way flying, AMPRs keep haunting me. I just flew 3 corners, B. Only one more left in the key. Chat boss, you don't get like me. No, you don't get like me.